This talk's title is Closed Form Error Propagation on SEN3 Group for Invariant EKF with Applications to VINS. This is my paper's outline. Now let's start from the introduction section. Our topic focus on the pose estimation. What is the pose? The pose in robotics involves a relative position and orientation which can be represented by an element of a Lie group. Pose estimation problem is essential for many industrial applications. There are many methods-based filtering and optimization to solve this estimation problem. Many optimization-based methods are also used in many iteration steps. It is not computationally efficient. So now the filter-based method is efficient to use for once iteration. As we all know, with the covariances being known, the Kalman filter is the best possible linear estimator in the minimum mean square error sense. Pose dynamics is nonlinear system. To deal with this problem, most methods mainly take advantage of the linearization to solve this problem. However, local linearization caused at an inaccurate estimate leads to significant errors and inconsistency. Now, we will concern about two problems. The first problem is that if the error dynamics with state being in the vector space is a nonlinear system, can we find a linear dynamics with being equivalent with this one, and how? The second problem is that if the error dynamic is nonlinear system with the process noise, how does this noise affect on the dynamsis? The answer is that Barao has found linear dynamics of nonlinear error in the case of noise-free in the invariant extended Kalman filter, IEKF. We will give another view on the first problem and reveal the noise term without approximation. Before showing the result, we will give some basic knowledge about a Lie group. This page is about the definition of the hat operation, exponential mapping and logarithm mapping. This page is about the definition of some common group SO3 and SEN3. In this talk, we will focus on the SEN3 group. For the state with being on the Lie group, its binary operation is just multiplication. So we will use two errors of this form. The left invariant error means when you add another left action on these two states, it doesn't change the error. That is, if you will multiply left by the same matrix, the value doesn't change. So is the right invariant error. We will introduce the linear group system. If the system satisfies the following property, its Lie logarithm with being a vector can be a linear system. Now we will introduce the following result. We will get interested in the following class of system. It consists of three parts. The first part represents that the control input relative to the body fixed frame governs this dynamics. The second part represents the one relative to the global frame, and the third part represents an autonomous part. The mapping F doesn't include any control input. It has a good example in the application of IMU dynamics. We calculate its invariant error propagation. Thanks to the linear group system property, we observe that this dynamics satisfy the property. So we can have the linear propagation. And this nonlinear error is its Lie logarithm. We will give a theorem on the closed form of the dynamic of its Lie logarithm. When we consider the noise, we have the following equation. The dynamic is not a linear group system. Now what is its Lie logarithm dynamics? We give the following theorem on the dynamic with noise. In this theorem, we have seen that the noise term is a nonlinear term. Barao said that when the logarithm error is close to zero, it can be approximated as a linear system. Different from them, our main contribution is that we use the derivative to reveal what the noisy system is. Now let's see the error propagation in an example of IMU. IMU state can be modeled as the state involved in the group. Now, let's consider the IMU dynamic. It can be written into this equation. Now let's consider the estimator. The main difference is that the control input is the measurement of the IMU minus the estimated bias. We compute the right invariant error propagation. We can get the dynamic of its Lie logarithm. This error dynamic can be helpful for us to compute the propagation covariance. The solution of the equation depends on noise term, causing mathematical difficulty in analysis. For estimation purposes, we will discuss on the following different approximations for the uncertainty propagation in an IMU. The first one is that we use the first order approximation. Approximation as we do in the first case leads to inaccurate covariance propagation when Xi is large. To tackle this problem, we propose to use an additional variable, termed Xi delta, drawn independently from some certain distribution to replace Xi. We will apply it into the VINS model. Now we will use our invariant error propagation into the filter-based method that can be used into the VINS. This is the evolution of this invariant error at the propagation step and update step. The error at the propagation step has been discussed. Now we observe the update step. When we left multiply the inverse of true state xt, we can derive this equation. The second figure is the root mean squared error, and the third one is the normalized estimation error squared. As shown in the third figure, the IJIEKF and IEKF maintain consistency, while the EKF is not consistent. We have tested our method in the IROS22 dataset. Let us see the video. The right figure is the evolution of root mean squared error. The green line represents our method. It illustrates that our method performs well during the whole experiment, especially at the end of the experiment. Note that it improved the performance of IEKF. The box plot of translation error statics illustrates that the center of the error distribution of the IEKF and IJEKF is closer to 0, and the IEKF performs better than the QEKF and FEJ in most sequences. And IJIEKF performs better than IEKF. All the evaluations are summarized in the table. It can show that IJEKF works better in most datasets. To conclude, this topic mainly talks about a closed-form expression on a linear group system and the one adding the noise. And we also provide the experimental result to show that the filter that uses this invariant error propagation can improve the filter performance.